This is part 3 of the lecture on one-dimensional motion with constant acceleration. In this final portion of the lecture, let's go ahead and take a look at the following example. Copy it down into your notes. Okay, a car is initially traveling at a speed of 100 kilometers per hour. Convert this initial velocity to meters per second. The car undergoes an acceleration of -1 meter per second squared for 5 seconds. What is the final velocity? Later on in the problem, we'll also calculate the distance traveled by the car. Let's immediately employ the method for solving a physics problem. If you recall, the first step is to draw a simple diagram. Okay, so right here, for example, is the car to begin. Right here is the car at the end of the problem. Okay, and then the next thing to do is to write down the known quantities. Once again, even though it's not explicitly stated so in the problem, let's just immediately assume that the car starts at the origin. So then therefore the initial position, x0, is equal to 0. Okay, now the initial velocity of the car is given as well. The initial velocity v0 is given to us as 100 kilometers per hour. Let's convert this into the base units of meters per second, as it's asking us to do in part A of the problem. So in part A of the problem, v0 is 100 kilometers per hour, and now let's go ahead and convert this into meters per second. There are, for example, 1,000 meters in a kilometer. So let's then multiply by the following. 1,000 meters per kilometer, and notice that the kilometers cancels out. And then the next thing that we'll do is we'll convert the hours into seconds. I'm actually going to do this in one step. There are, for example, 60 seconds in a minute, and there are 60 minutes in an hour. 60 times 60 is 3,600. Therefore, there are 3,600 seconds in an hour. So let's go ahead and convert hours into seconds by using that conversion factor in one step. Here's how I'll go about doing that. I'm going to multiply by 1 hour per 3,600 seconds. Once again, 60 times 60 is 3,600, 3,600 seconds in an hour. Notice the hours cancels here and here, and then the units I'm going to end up with are meters per second. So then therefore, I take the initial speed of 100 kilometers per hour, and then I multiply by 1,000, and I then divide by 3,600. Once I do this process, I'll round off the answer a little bit. I end up with 27.8 or so meters per second as the initial velocity. Okay, and then we have some unknowns here in the problem, and there is, by the way, one more known quantity I neglected to write down, actually 2 more in part B of the problem. We are given the acceleration and the time, so let's go ahead and write those down as well. Okay, now the acceleration, you'll notice, is given to us as a negative number, -1 meter per second squared. What that means is that the acceleration vector points to the left-hand side. And here's why that is. Let's take a look and see what happens with the car at the end of the problem. At the end of the problem, the car is going to have some final velocity v that is one of the unknowns. Notice that I'm drawing this final velocity vector as being smaller than the initial velocity vector v0. The reason for that is as follows. Recall the tail-to-tip method of vector addition that describes the following expression. The initial velocity plus the change in velocity is equal to the final velocity. So let's take a look at the 2 velocity vectors that I've written down. Right here is the initial velocity vector. Right here is the final velocity vector. Where on this simple diagram, using the tail-to-tip method of vector addition, is the change in velocity vector delta v? It's right here, like so. Notice what happens when I pantomime this. We have the initial plus the change is equal to the final. The change in velocity vector delta v points to the left. Recall that acceleration is change in velocity divided by change in time. So then therefore, if the delta v vector points to the left-hand side, this then means that the acceleration vector points to the left-hand side. That's what the negative sign means. The negative sign doesn't mean necessarily that the car is slowing down. No, instead it means that the acceleration vector points to the left-hand side. Sometimes in a situation such as this, where the object is slowing down, we tend to use the word deceleration. That's perfectly fine. You can go ahead and use that word, but the word deceleration is a context word. It has no mathematical meaning. Instead, mathematically, we do have here a changing velocity for this car with respect to time, therefore there is an acceleration. The acceleration vector points to the left-hand side. The negative sign indicates that for us here in this problem. Okay, and then lastly, in terms of the known quantities, as I stated earlier, we are also given the time. The time t here is given to us as 5 seconds. So now I've written down here all of the known quantities, the unknown quantities, and I've drawn a simple diagram. And now let's go ahead and solve the problem in earnest. Okay, so in part B of the problem, it's asking us for this final velocity, and later on, by the way, in part C of the problem, we're also going to calculate the distance traveled by the car. That's this unknown position vector x like so. All right, next thing that we have to do is write down the relevant equations. Okay, so we have position as a function of time, and we have velocity as a function of time. Even though this seems to be a completely different physical situation than the rocket problem from the previous portion of this lecture, it's actually not. The two situations are physically very similar to each other in the following sense. They are both one-dimensional motion with constant acceleration, so then therefore the same kinematics equations that I employed for the rocket, they are employed here as well. Okay, and now we get to the math. With respect to the math here, mathematically this is a slightly more difficult problem than the previous example. Let's actually begin by taking a look at the velocity equation. In the velocity equation, there's actually no algebraic steps to perform here because we actually already know all of the quantities that are here on the right-hand side of the expression. So let's just go ahead and plug in everything, and then ultimately we'll then end up with our answer for the final velocity v. So I'm just going to plug in. Right here I plug in the initial velocity v naught of 27.8 meters per second. So let me go ahead and do that here. Okay, and then plus -1 for the acceleration, and then multiply by the time here of 5 seconds. And I end up with a final velocity here of 22.8 meters per second. Notice that the magnitude of this final velocity vector is in fact less than the magnitude of the initial velocity vector. Once again, that's because that delta v vector points to the left-hand side. Okay, and then lastly here for the problem, let's go ahead and find the final position x. There's no algebraic steps to perform here. In this case, all that we have to do is plug in everything into the expression. This will be part C of the problem. Okay, now we have x naught, which is equal to 0, and then I have here plus 27.8 times 5. So let me go ahead and do that first. And then using the negative sign is plus 1/2 times -1 times then 5 squared. So plus 1/2 times -1 times 5 squared, and ultimately the distance traveled by the car, is 126.5 meters. So algebraically, this actually turned out to be a rather easy example. We already have all the information on both sides of the expression here and here, and then therefore all that we had to do was plug in and calculate correctly. Okay, this concludes the lectures on one-dimensional motion with constant acceleration.